So today I'm going to try and get through mass spectroscopy with you. Now, mass spectroscopy is an analytical method, as I'm sure you've gathered.
Yeah.
And from the name, mass, obviously you're measuring masses.
Yeah.
And spectroscopy means you're kind of still doing some sort of, sort of spectrum. Now, it's going to be very, very different to all the things we've covered before. We're not talking, it's not the same as, absorbing anything. It's not like AAS or IR or UV or AES or anything like that.
No.
But it is in some ways still some kind of spectroscopy, sort of, but not in the way we've described it in the past.
Yeah.
So treat it like a new thing because it is a new thing.
Yeah.
Now, when you talk about mass spectroscopy for your exams, you could basically get two types of questions, essentially. One is basically going to ask you about how it works. So you need to sort of have some understanding of its design, how it's the basic principles behind it and how it works. Kind of like what we did with AES. You need to know that stuff. And the other, of course, is they give you the result and, your job is not to understand how it works, but to interpret it. And, we've done similar with IR as well and AES and so on. Now, I'm going to spend a fair bit of time to go through the how it works part because I think that will be very, very, very foreign to you. But you do need to know that. Okay.
Yeah.
So we're going to go through some physics principles. You understand that particles can have charge, right?
Yeah.
What type of charges can they have?
Positive or negative?
Clearly, right? And if it's positive, what type of thing is positively charged?
Proton?
Can you give me any other examples?
Positive. Cation?
Yep. Any cation is basically going to be positively charged. Protons, electrons.
Negative?
Or example?
Like an anion?
Right. Okay. So you've got positive and negative charges. Now, when something is charged, how do they interact?
They either attract or repel each other.
Depending on?
The charges.
And what about the charges in particular?
The like ones repel and the different ones attract.
Yeah, exactly, right? So you can either have positive and positive, which will repel, or you can have negative charge and negative charge, which will also repel, and that's your like charges repel. Or you can have, opposite charges, positive and negative, and they'll attract. And that, I think, is all pretty sort of easy for you. But what you might not be as comfortable with potentially is, do you know how, why a positive or a negative charge can attract or repel? Why, if I have a positive charge and a negative charge,
yeah,
and we know that they attract each other,
yeah,
but why does that happen? How do they need to touch each other to attract each other?
No.
So how can this force, which is called a non-contact force, so the electrostatic force is a non-contact force, how does this negative charge experience the force from the positive charge?
How it's magnetic force?
No, it's not a magnetic force, actually. It's not a magnetic force.
Kinetic? I don't know.
Okay, so this is getting more into physics, and I won't spend I'll spend a decent amount of time on it, but really, we're basically saying charges exert force on each other by the fact that this charge will create a field, and the field then exerts the force on the negative charge.
Yeah.
So the positive charge creates an electric field, and it's the electric field that will, exert a force, right?
Yeah.
Now, if you've got a positive charge and you've got a negative charge, hypothetically a negative charge 1 and negative charge 2, do you think they'll experience the same field strength? Will they be attracted as strongly as each other?
No.
No. So basically, without getting into it too much, the force that a proton exerts on charged particles depends on the field strength, And as you can quite clearly guess, the further away you are, the less you're attracted, which means the field strength is or is not uniform.
Yeah.
Is it?
It's not uniform.
Is not uniform. Exactly. So if you have a charge, it does not give you a uniform electric field. Now, that makes things a bit more complicated for us. We don't want that.
Yeah.
When we're doing an experiment, ideally we want to be able to, well, control things. So we want a uniform electric field. And that is created by using two parallel plates over here.
Yep.
So these two parallel plates are parallel. You connect a voltage to it, so a battery basically.
Yep.
The battery will have a positive end and a negative end. This positive end will pull out the electrons, making this side positively charged when it was uncharged before. The negative end will push in electrons, and so it will make this side negatively charged. So you'll have a positive and a negative.
Yep.
And we'll create this so-called electric field that I've drawn here in blue.
Yeah.
And this blue part is uniform inside between the electric plates. And it'll be not uniform outside, but we don't really care that for our purposes. We'll be doing our things inside the sort of uniform area.
Yep.
Now, you don't need to know the formula. That's the formula for how to calculate. You don't need to know that. But there's this sort of electric field here.
Yep.
Now, imagine you're a proton in this electric field. What would happen to you?
You'll get repelled by the positive plate and attracted by the negative plate.
Which means you will?
You will go through the magnetic field.
There's no magnetic field here. There is no magnetic field at all.
Oh, you.
There is no magnetic field here right now. I've got a positive charge here. What would happen?
They'll get repelled by the positive plate.
Yep. And attracted to the negative plate. So
Yeah.
it would?
It would clash.
Well, it will go down, right?
Yeah, yeah.
And it will probably reach the negative plate. But the point is, it's going to experience a force. So repulsion and attraction are forces. It'll experience a force going down. And so it'll go down.
Yeah.
Are you happy with that?
Yeah.
So are you happy with the fact that a charged particle can experience forces from an electric field?
Yeah.
And positive charges will follow the direction of the electric field, and negative charges, which you don't really need to worry about for the context of chemistry that we're about to do right now. But so all the stuff we're doing is going to be positive charged, but it'll go the other way. All right. Are you happy with that?
Yeah.
Okay, good. So the key thing I want you to get out of that is electric fields exert forces on charged particles, and it's very simple. If it's positive, it goes towards the negative. End of story.
Yeah.
Happy with that?
Yeah.
Now, there is a second one we need to consider, the magnetic field. Do you know what a magnetic field is? Do you know what creates a magnetic field? What's it related to?
Magnet. The magnet.
Right, it's about magnets, north and south pole and that kind of thing, right?
Yeah.
So the magnetic field's about magnets. Do they affect charges as far as you're aware? Do magnetic fields, so magnets like iron, north, south poles,
Yeah.
do they affect charges as far as you're aware?
Oh no.
Right, so you're not aware of anything. And that's because you don't do physics. And you would have done this in year 12 physics kind of thing. But that's the other thing I kind of need you to be aware about. So magnetic fields do have effect on charges, but there are conditions to be met, all right?
Okay, yeah.
And that's what we kind of need to talk about here. So if a magnetic field, it has a formula, I'm not going to derive this and so forth, but basically there is a force, and that force is equal to QVB. There's a sine theta as well here, but I'm just ignoring that because it's not really relevant for your purposes, all right?
Yep.
So you've got the 4F, which is the force on a charged particle by the magnetic field, is equal to Q, which stands for the charge, times V, which stands for the velocity, and B, which stands for the magnetic field strength.
Yep.
Are you happy with these?
Yeah.
All right. So let me ask you, if I want the force to exist, if I want a magnetic field to exert a force on a particle, what conditions have to be met?
There's a charge, there's a velocity, and the magnetic
Right.
field.
So you actually have to have a magnetic field, right? You can't not have a magnet there, right? So we assume there's a magnetic field, but you're saying that there has to be a charge, which
Yep.
means, in other words, the particle needs to be,
An ion.
it needs to be charged,
Oh yeah.
right? So an ion would fit the bill, would work, but it needs to be charged. It can't be neutral, right?
Yep.
And you said it has a velocity. What does that mean?
It's moving.
Exactly. So for a magnetic field to exert a force on a particle, we require, obviously, the fact that you have a magnetic field in the first place, but you need the particle to be charged. Positive or negative doesn't matter here right now.
Yep.
And it needs to be moving. But if a particle is charged and it is moving, then it will experience a force from the magnetic field. Are you happy with that?
Yep.
All right. That's the key, one of the key points I need you to understand. That is, magnetic fields can and do affect particles that are charged and moving. You don't need to know the formula necessarily, but in some ways it will be helpful, not necessarily for the formula, but I mean, what you do want to know is kind of ideally the sort of relationships. So, you know, the more charge, the stronger the force, the faster it moves, the stronger the force, the stronger the magnetic field, the stronger the force.
Yep.
Is everything clear so far?
Yep.
Okay. Now, force is what we call a vector. And what I mean by that is that it has both a magnitude, which we are calculating using this formula, but it also has a direction.
Yep.
So a vector has basically magnitude and direction. So basically a force, it's like a push or a pull, but whether you're being pushed forward or pulled backward is different. So we kind of want to identify the direction of this force. Now, identifying the direction, admittedly, is not so important for your chemistry, not as important, but
Yep.
to try to make things make sense a little, I'll just briefly go over it here, but don't pay attention to it too much. Like, don't worry about it too much if you're struggling with this.
Yep.
To determine the direction of force of a magnetic field on a charged particle, you hold your hand out. Notice it's your right hand. It's called the right hand palm rule.
Yep.
And you basically just, you know, hold out your hand flat and make sure it's the right hand. The thumb is the velocity of the positive charge. Your fingers point in the direction of the magnetic field. And if I've got my right hand like this, I've got my palm pushing sort of out of the page, right?
Yep.
And so that push, think of your hand as pushing, that's the force.
Yep.
which means that if I have a situation like this, where my charged particle is positive, notice it's a positive charge, it has to be a positive charge. Negative would be the opposite, okay? If I've got a charged particle that's positive moving upward, magnetic field moving leftward,
Yep.
I would put out my right hand, like kind of withdrew on the board there, and it would sort of push out of the page. And that means this positive charge would experience a force out of the page.
Yep.
Are you happy with that?
Yep.
Good. So we've established that a charged particle can experience, effects from an electric field. Electric field can give a charged particle a force. And we can also say that a charged particle, if it's moving, will also experience a force by a magnetic field. Yeah?
Yep.
We're now going to start talking about what happens more specifically to a charged particle in a magnetic field. Now, I'm not really going to go through the derivations too much with you here, but if you think about this, and you might not know this, but if you have a positive particle moving in here, right?
Yeah.
Can you quickly work out for me what's the direction of the force?
Going into the page?
Actually, no, it's not into the page. So into the page is this thing here, and that's your magnetic field. So your magnetic field is going into the page.
Oh.
Your velocity is going to the right, so it's a positive particle.
Yeah.
So if it's a positive particle going to the right, and this is into the page, then
It's going upwards.
well, the force is going upwards.
Yes.
So indeed, the force will be pushing up. Now, I know you didn't do physics, but perhaps you might know this from science. If you experience a force, what's going to happen to the particle?
Move.
Well, if it wasn't moving, it will move. But if it is moving, what will happen to it?
Accelerate.
Yeah, it will accelerate, exactly. It will accelerate. And accelerate could either mean it starts moving faster or slower, or it could change direction. Does that make sense?
Yeah.
Now, you won't know the rest of this, so I'll basically just tell you. But that means it's going to start changing sort of direction, kind of, like this, or like this, or like this, right? It's going to change upward in some way, yeah?
Yep.
Now, you wouldn't have done the work for it, so you'll just have to just basically take the result here. But basically, the message I want you to get is if a charged particle enters a magnetic field and therefore experiences a force from the magnetic field, it will undergo circular motion. It will move in a circle.
Yep.
Now, you won't have done the sort of theory for me to explain this properly, so don't worry. Just understand, if a charged particle enters a magnetic field, it will start moving in a circular fashion.
Yep.
And that's what I'm saying here. Moving charged particle in a magnetic field becomes circular motion. Now, of course, this circular motion means that there's a radius associated with it, right?
Yep.
Because it's a circle. So there's a radius. So, I mean, I'm very, very briefly, deriving it here. You don't need to worry about any of that too much, all right? You wouldn't have done this. This is called centripetal acceleration. You've got your FB equals QVB, and your FC equals MVR squared over R, and those need to be equal, and so on and so on. And the point is, the radius of this circle can be shown to be M times V over QB. Now again, it's not so much the formula that matters. You don't need to memorize this formula at all. What is important though, is that you understand what factors affect the radius and in what way.
Yeah.
So the formula can help you understand that potentially. And that's why I kind of feel like writing it out might help you.
Yeah.
But note that at no point do I expect you to memorize the formulas necessarily. For chemistry, that's not necessary.
Yeah.
But I do expect you to understand, okay, if my particle got heavier and nothing else changed, what would happen to the radius? If my particle charge changed, what would happen? If the velocity went faster, if it's slower, if the magnetic field is stronger.
Yeah.
So I don't expect you to memorize the formula. Excuse me. I do expect you to understand the factors that would affect it, the radius. And given the formula is mv over qb, then clearly the factors are m, which is the mass of the particle,
Yep.
v, which is the velocity of the particle, q, which is the charge of the particle, and b, which is the magnetic field strength. It's the strength of the magnetic field. And I think it's quite clear to you, but let's write it out. If m goes up, what happens to r?
Goes up.
If v goes up, what happens to r?
Goes up.
If q goes up, what happens to r?
Goes down.
If b goes up, what happens to r?
Goes down.
And you'll understand why I'm talking about this in a moment, but let's say if m over q goes up, what happens to r?
Goes up.
Exactly. So those are the factors and their trends. Are you happy with everything so far?
Yeah.
Good. Well then, that's basically what I've got there.
Yep.
Now, what we're really going to do now is basically consider how is all these, I've spent a little bit of time going through this, but how do these principles apply to mass spectroscopy? I mean, you don't do physics. So, well, why did we spend time going through all of that, right?